Have you ever looked up at the night sky and wondered, where did it all come from? The stars, the planets, even the vast emptiness of space, they all came from somewhere. But where? This question has led us on an incredible journey of discovery. For centuries, philosophers and theologians pondered the origins of the universe. With modern science, a new narrative emerged. The Big Bang Theory explains a universe that began from an extremely hot, dense state. But how did we arrive at this theory? What evidence supports it? Let's delve into these questions and explore the fascinating world of cosmology. The Big Bang Theory is the prevailing cosmological model for the universe. It describes the universe from its earliest known periods through its subsequent large-scale evolution. The universe originated from an extremely hot, dense state, approximately 13.8 billion years ago. Space has been expanding since, resulting in the universe we observe today. The Big Bang wasn't an explosion, but the rapid expansion of space itself. Imagine a tiny balloon inflating rapidly. That's a closer analogy. The Big Bang Theory remains our best explanation for the universe's origin. One of the most compelling pieces of evidence supporting the Big Bang Theory comes from a faint afterglow of light that permeates the universe. This light, known as the Cosmic Microwave Background Radiation, or CMB, was discovered in 1964 and has been studied extensively ever since. The CMB is often described as the echo of the Big Bang. It's a faint, uniform glow of microwave radiation that comes from every direction in the sky. This radiation is thought to be leftover heat from the Big Bang itself. As the universe expanded and cooled, this radiation stretched out, shifting its wavelength into the microwave portion of the electromagnetic spectrum. The CMB provides a snapshot of the universe as it was just 380,000 years after the Big Bang. It reveals a universe that was incredibly hot and dense, just as the Big Bang Theory predicts. By studying the tiny fluctuations in the CMB, scientists can learn about the early universe's composition, density, and temperature. The discovery of the CMB was a major triumph for the Big Bang Theory. It provided strong evidence that the universe had a hot, dense beginning, as the theory predicted. Another crucial piece of evidence supporting the Big Bang Theory comes from the observation that the universe is expanding. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery. He observed that galaxies are moving away from us, and the farther away a galaxy is, the faster it is receding. Hubble's observations implied that the universe is not static but is in fact expanding. This expansion is a key prediction of the Big Bang Theory. As space itself expands, the distance between galaxies increases, making it appear as if they are moving away from us. Think of baking a loaf of raisin bread. As the bread bakes and expands, the raisins embedded in the dough move farther apart from each other. Similarly, as the universe expands, galaxies move farther apart. The expansion of the universe is not just a visual illusion, it's a fundamental property of space itself. This expansion has been confirmed by numerous observations, including measurements of distant supernovae, which act as standard candles for measuring cosmic distances. Section 5. Before the Bang Mysteries and Speculation. While the Big Bang Theory describes the evolution of the universe from a very early state, it doesn't tell us anything about what caused the Big Bang or what, if anything, existed before that moment. The question of what came before the Big Bang is one of the most profound and challenging questions in cosmology. Some physicists believe that the Big Bang was not the beginning of time, but rather a transition point from a previous phase of the universe. One intriguing idea is the concept of a big bounce, where the universe undergoes cycles of expansion and contraction. In this scenario, our current expanding universe could be just one phase in an eternal cycle of cosmic evolution. Another idea is the concept of inflation, a period of exponential expansion in the very early universe. Inflation theory, proposed in the 1980s, attempts to explain some of the puzzles of the Big Bang model, such as the remarkable uniformity of the cosmic microwave background radiation. However, it's important to note that these ideas are highly speculative. We currently lack the observational data to test these theories and determine whether they accurately reflect the true nature of the universe. Section 6. Alternative ideas, other universes, other theories. While the Big Bang Theory is the prevailing cosmological model, it's not the only theory that attempts to explain the origin of the universe. Some alternative theories challenge the Big Bang's fundamental assumptions or offer different explanations for the observations we see. One alternative theory is the steady-state model, which proposes that the universe has always existed and has no beginning or end. However, this theory has largely been discounted due to the overwhelming evidence supporting the Big Bang, such as the cosmic microwave background radiation and the expansion of the universe. Another alternative idea is the concept of a multiverse, where our universe is just one of many universes existing simultaneously. The multiverse hypothesis arises from some interpretations of quantum mechanics and string theory. However, there's currently no direct observational evidence to support the existence of a multiverse. It's essential to approach alternative theories with an open mind, but also with a healthy dose of skepticism. Extraordinary claims require extraordinary evidence, and the Big Bang theory remains the most well-supported explanation for the origin of the universe based on the available data. Section 7. The Genesis of Life, from Stars to Cells. While the origin of the universe is a profound mystery, the origin of life within that universe is equally captivating. How did life arise from non-living matter on our planet billions of years ago? This question has puzzled scientists for centuries, and while we don't have a definitive answer, we've made significant strides in understanding the processes that might have led to life's emergence. The prevailing scientific hypothesis is that life arose from non-living matter through a process called abiogenesis. Abiogenesis is the natural process by which life arises from non-living matter, such as simple organic compounds. While the exact mechanisms of abiogenesis remain elusive, the prevailing scientific hypothesis involves a series of steps, from the formation of organic molecules to the emergence of self-replicating systems. These self-replicating systems, likely RNA molecules, eventually gave rise to DNA, the blueprint of life as we know it. Over billions of years, these simple life forms evolved and diversified, eventually giving rise to all the plants and animals we see today. The study of abiogenesis is a complex and challenging field, but scientists are making progress. By recreating the conditions of early Earth in laboratories and studying extremophiles, organisms that thrive in extreme environments, scientists are piecing together the puzzle of life's origin. Section 8. The Search for Meaning, Our Place in the Cosmos. The vastness of the universe and the intricate processes that led to our existence naturally raise questions about our place in the cosmos. Are we alone in the universe? What is the meaning of life in the grand scheme of things? While science can provide insights into the physical processes that govern the universe, questions of meaning and purpose often lie outside the realm of scientific inquiry. The search for meaning is a deeply personal journey, and different individuals and cultures find meaning in different ways. Some find solace in religion and spirituality, while others find purpose in their relationships, their work, or their contributions to society. Regardless of our individual beliefs, it's undeniable that we live in a remarkable time. For the first time in human history, we have a scientific understanding of the universe's origin and evolution. We can trace our lineage back billions of years to the very first stars that formed in the universe. This knowledge fills us with a sense of awe and wonder and underscores our interconnectedness with the cosmos. We are, in a very real sense, children of the stars, formed from the same cosmic dust that gave rise to everything we see around us. Section 9. The Never-Ending Story, The Future of the Universe. Just as the universe had a beginning, it will also have an end. The fate of the universe is ultimately determined by the interplay of gravity and the expansion of space. The current expansion of the universe is driven by a mysterious force called dark energy, which is causing the expansion to accelerate. The ultimate fate of the universe depends on the nature of dark energy. If dark energy continues to accelerate the expansion of the universe, as it is currently doing, the universe will continue to expand forever, becoming increasingly cold and diffuse. This is known as the Big Freeze scenario. The discovery of dark energy and the accelerating expansion of the universe has profound implications for our understanding of cosmology. It suggests that the universe's evolution is far from over, and that we are living in a dynamic and ever-changing cosmos. As we continue to explore the universe and unravel its mysteries, we can be sure that new discoveries will continue to challenge our understanding and inspire us with awe and wonder. The story of the universe is a never-ending story, and we are privileged to be a part of it.